Okay, hello guys. So this will be your um a lecture. So we are on 14.3, the partial differentiations, partial derivatives. This will be the starting point of you guys doing differentiation in a multidimensional setting. So let us be careful with this. Let's go through this step by step. Right. So first of all, let's introduce the definition of partial differentiation. After this definition, I will explain how are this definition working. So again, let us assume that f is a two-dimensional function. So you have a variable within some domain D in a R2 setting, so x and y, say, per se, where it is a function, so the value lies within R. Then the two partial derivatives at the point AB, of course, belongs to the domain, are defined as follows. The partial differentiation of f with respect to x at the point AB is defined to be this limit. So there's a lot of things to explain. Let us do this slowly. This is f of a plus h and b. So we are perturbing a by a small distance of h. You can either go left or right, depending on whether h is zero or not, whether h is positive or not. And we subtract that thing by f of ab and divide it by h. So it looks very much like the original definition of limit in the one-dimensional case, right? Only in this case, we're fixing the second variable to be b. Also, this notation here is usually pronounced del, but you can also just say something like partial f partial x. It's okay. Everything works. The only reason that we use this del notation is because we want to differentiate it. We want to make a difference of this guy and this guy. This is a single variable case, and this is the multi-variable case. Okay. So basically, partial differentiation with respect to x is simply calculating the differentiation of f in the x coordinate. And the same thing happens for y, right? There's a bunch of notation for partial derivatives. In most cases, we will either use this notation or this notation. So we can see there's a sub x here. We put the x in the sub index. So fx means we're differentiating f with respect to x. And the same holds for y. And these two guys are called the partial derivatives of f as a two-dimensional function. You can naturally extend this definition to a multi-dimensional function, where in an n-dimensional space, you'll have n different partial derivatives with respect to x1, x2, all the way to xn. Okay, now let's kind of view this geometrically. We know that the derivative f prime in the one-dimensional case actually has a geometrical meaning, which is the slope, right? It is the same for partial differentiation, actually. So let us see. In this three-dimensional setup, if this surface is the graph of z equals to f of xy, at the particular point AB, the function value is f of AB, right? So the point on the surface will be A, B, f of AB. Now, if we move along x, then the point here moves along the surface in the x dimension, right? In this case, the vertical dimension. So we're actually trying to investigate the behavior of the single path here at the point AB, f of AB. Similarly, if you move around the y coordinate, in this case horizontally, then you'll get this kind of behavior, right? So we're investigating how the value of the function changes when you go through a little bit around this y direction. So in conclusion, the x directional partial derivative studies the f when it changes in the x direction. And similarly, the partial f partial y studies the change of f in the y direction. So to be more precise, we can actually find a set of like tangent lines at a point in the x direction and y direction, which we will do just now. So first of all, let us give an example on how to evaluate this partial derivatives. And then we'll go to a geometrical picture. So first of all, let us set f of xy to be a two-dimensional function, which is given by x cubed y squared. So by definition, The partial differentiation with respect to x is simply plugging x to be x plus h and subtract x squared, x cubed, y squared. Now here, y squared is actually independent of the limit, right? So we can factor it outside. Y is just a constant. And you have this guy. And this is really familiar, right? This is actually just the definition of the differentiation of x cubed. Note that I use a d here because it is a single variable differentiation. And now we get 3x squared y. So the spirit of computing the partial differentiation is simply regarding any variable except the variable that you're differentiating as constant, in this case, y. So for instance, if you want to compute the partial derivative of y, so in the partial derivative of f respect to y, then you treat this x cubed as a constant. So we're simply differentiating something like 4y squared. Then you get 4 times 3y, right? Sorry, 4y squared, so sorry, 2y. So that is exactly what you get. You get x cubed times 2y. So this is an important principle. While you're computing a partial differentiation, you simply do a single variable derivative when you're regarding any other variable to be a constant. So as we promised above, you can actually find the so-called tangent line at the point in some particular direction. In this case, let us find the x direction tangent line. So we know that along that line, you have a partial derivative of f being 3x squared y. Let us investigate a particular point at 1, 2. So on the surface, the point is 1, 2, 4, where 4 is the function value for f of 1, 2. So we have a point, right? Now we need the directional vector. As mentioned in the video in 12.5, we need a point and a directional vector to find out the either parameterized version or a symmetric equation for the line. How do we figure out the directional vector now? We know that the line is actually parallel to the xz plane because the y coordinate is not moving, right? We are not investigating the y direction. The y is actually always fixed to be 2 in this case. So how about the x direction and z direction? By the definition of partial differentiation, we know that whenever x, actually, let me draw this way. Whenever x goes by 1 unit, then by definition, it goes either upward or downward, depends on the signature. It goes upward or downward by this much of units. So that makes the slope to be 1 and fxab. So the actual vector of the direction is in fact simply fx ab 0 in a y coordinate and 1 in a z coordinate, actually. Right? So you can compute those. Oh, sorry. I'm writing this incorrectly. It should be 1 in x coordinate and 0 in the y coordinate and fxab in a z coordinate. Because whenever x goes 1 unit, then z goes upward or downward by fxab unit. So let us compute this. We know that z is always equal to this guy, which is the slope of x minus 1 plus the original 0.4, and y is fixed to be 2. We can conclude those guys by this formula. X equals to 1 plus t, y is always 2, and z is given by 4 plus 16. So you see that the directional vector is just 1, 0, and 6, which is what I mentioned. 1, 0, and fx AB. In this case, AB is 1, 2. Right? So now we find a directional tangent line in the direction of the parallel to the xz plane, which is tangent to the surface at the point 1, 2, 4. You can see that it is not really enough to find that type of tangent line because there's actually a tangent plane. There's infinitely many different tangent lines surrounding that point, which we will be covering next section. But this is just a demonstration of how partial differentiation works geometrically. It actually provides you a kind of a directional vector along some particular direction, in this case, the direction which is parallel to YZ plane that is tangent to the surface. Okay, So now let us provide some example about the computation of partial differentiation so that you guys are familiar with this type of algorithm. So the first function is x times sine xy. As we mentioned before, if you want to evaluate the partial differentiation along x, then we regard y as constant, something like 2 or 3 or 4. So you have two functions. You do the product rule. You have x. Oh, you have x being differentiated by x. That's 1. So 1 times sine xy. That's the first term here. And you keep the first term and differentiate the second term. Where by the chain rule, you get cosine xy first, and the differentiation of xy is just y, right? So just regard this as sine of 2x. Sine of 2x give you cosine 2x times 2, right? The 2 is just y here. And for the y differentiation, the derivative of x respect to y is just 0. It is a constant, right? So we differentiate this guy, which is cosine xy times x. Right. As for this function, it is a three variable function, but you do the same thing. If you're treating x as a variable, then this is actually a polynomial, right? Yz is something like 2 or 3 or 4. So you're actually differentiating this guy. And so by a polynomial differentiation rule, you get the partial derivative of f is simply yz, which is why you drop down the power, right? And you get yz minus 1. If you're treating yz as a variable, then you're dealing with exponential function. It is something like this. So you can memorize the rule of that differentiation, or you can just reduce everything into exponential. So if we write xyz into exponential of yz ln x, then by differentiating respect to y, you get again by chain rule. The first thing here is here because the differentiation of ex is just ex, right? And then you differentiate the power, the exponent, which you get z ln x, because this is something just like y times 2. 2 is z ln x, so you get 2. Combining those things, you get z ln x together with the original function. The same thing happens for z because in this case, y and z are symmetrical. So you get the same thing, xyz times y ln x. So you can see that it behaves really differently in x and yz. In yz, it is like exponential. In x, it is like polynomial. Right. So for the next exercise, we're differentiating an integral, which you guys should be familiar due to the fact that in calculus 1, you guys have learned fundamental theorem of calculus, right? So differentiating an integral is always not that tricky. In this case, let's recall the nice Leibniz rule. This is a nice rule induced by the fundamental theorem of calculus. So whenever you're integrating a function f, in particular if it's continuous or satisfies some regularity property that you guys have learned in calculus 1, then this integral all the way from a of x, which is some function in x, all the way to b of x, which is some function in x, then the derivative of this whole thing in terms of a function of x is f of b of x times b prime of x minus f of a of x times a prime of x. The proof of this is very, very simple. I will postpone this to the supplement lecture, which you guys can see how we can do this via the first and the second fundamental theorem of calculus. So let us apply this to what we are going to do. If we are trying to differentiate this guy with respect to x, then it is actually the same thing as this, right? However, in this case, b of x is just x squared, where a of x is y. And that is actually a constant in regard of x, right? So we plug in the upper bound, we multiply the differentiation of x squared to x, and then we plug in a lower bound, where we multiply the differentiation of y respect to x, and that is 0. So we get this. The same thing happens for y. So in that case, b of y is x squared, where a of y is y. So this is a constant with respect to y. You get the first term vanishing, and you get cosine ey. Oh, I forget the signature here. Minus cosine ey. So that's all. If you apply the Leibniz rule, it is quite a fascinating result, which you can apply it for differentiating a integral. Right. So obviously, when we're introducing f prime, we subsequently introduce f prime prime, right? The same thing happens here, but now we have different versions of double derivatives. So we introduce this for different derivatives of the second partial derivatives of a function f. So now again, given a function, which is a two-variable function, the second partial derivatives of f at the point AB is given by these four guys. The first one is to differentiate f twice by x. So there's a bunch of notation going on here. Let us go step by step. You can either differentiate it twice by x as in this notation, which is defined to be this guy. So this guy is the first derivative, right? And then we differentiate again partially with respect to x. And then we evaluate it at AB. You can also do fxx as a notation. Now, things become tricky here. So if we differentiate y first, then x, then we denote the notation by this. Partial squared, del squared, del x, del y, right? So this is the tricky part. Because we're doing y first and then x, so we usually write this notation to be f of yx. So we do y first and then x. So this is actually the reverse notation of this del x, del y. So be careful with that. And we will soon see that the order is not really important, but that is for afterwards. Similarly, if you do the x differentiation first and you do the y differentiation after, then it is denoted by del squared f del y del x, right? And like I said, it is doing x first and then y, so we denote it by fxy. Lastly, it is the double derivative with respect to y. So you get del y or fy. And we can naturally generalize this to higher dimension and higher orders. For example, you can do, if you are dealing with a three-dimensional space, you can do fx, or y, or something like that. Right? Okay. First of all, let's do some example so you guys are familiar with the definitions. So let us define this function f of xy to be 2x minus 3y divided by x plus y whenever the denominator is non-zero. I do this example because I want you guys to be familiar with the quotient rule, which I think I haven't done it in the previous exercises. So let us do this. Obviously, to find the second partial derivatives, you have to find the first. So the partial differentiation of this function with respect to x is regarding y as a constant. So first of all, for quotient rule, you have to square the denominator. You differentiate the numerator, which is 2 in this case, and you multiply it by the denominator. Subtract by the numerator, the same thing, and you differentiate the denominator, which in this case is x plus y, and you get 1 when you differentiate it with respect to x. And then after some algebra, you get 5y divided by x plus y squared. The same thing happens for f1. Okay, now we just apply another layer of differentiation. So to differentiate, to obtain fxx, you just differentiate this guy again by x. So see that in this case, the derivative of the numerator is actually 0 because y does not depend on x, right? And you multiply the denominator, subtract by the numerator together with the differentiation of the denominator. In this case, it is 2x plus y multiplied by y. The 1 here is actually the partial derivative of x plus y together with x, the chain rule, right? So again, after some algebra, you get this nice notation. You can cancel this 2 by, but I just leave it there to be complete. Yeah, I don't want to get too much into the algebra here, but basically you can do the same thing. For example, if you want to compute the partial derivative fxy, then you differentiate fx by y again. As I mentioned, this order here is order in the sense of operations. So we do x first and then y. And this guy is the same as this notation. Okay, we do x first and then y. So be careful with those two notations. And we get this, which I encourage you to check the algebra afterwards. So one thing you can notice here is that these two guys actually the same, right? If you differentiate x first and then y, it is the same as if you differentiate y first and then x. So that is of no coincidence. This is actually a big theorem, not a big theorem, a more delicate theorem. It is called Clair's theorem. So let me state this first. For a function f, again, a two-variable function, you can generalize this to multivariable function. Then supposedly both of the derivatives, sorry, the double derivatives, fxy and fyx exist, and they're continuous as a function. Then those two derivatives must be the same. So that is what I said before, that the order does not really matter in some sense, provided that f is nice enough, in the sense that the mixed derivatives have continuity. And this is actually not that trivial. So we will see the proof in a supplement lecture video, right? So anyway, provided that kind of theorem, we know that in general, for nice enough function like polynomials, like trigonometric function, you can always expect the partial derivatives to be the same, disregarding the order. You can do xyx, yxx, xyx, yxx, or xxy. Those three derivatives will be the same, right? By Claire's theorem. Okay, so after that, let's see a counterexample of Claire's theorem. So by counterexample, I mean maybe there will be some function that does not have the same mixed derivatives. fxy is not fyx. So first of all, this function is defined by x cubed y minus xy cubed divided by x squared plus y squared whenever xy is not the origin. And you have the same definition to be 0 when xy is the origin. So first of all, part A asks you to find a graph, which is demonstrated here. You can see that it actually behaves nicely as 0. As we have mentioned in lecture 2, sorry, lecture 7, the 14.2 on the limit and continuity, we know that you can see the degree in the numerator is actually 4, and the degree in the denominator is actually 2. So the numerator dominates the denominator when xy goes to 0. It decays faster. So the limit of this function at 0 is actually 0. It is continuous at the origin. Part B asks us to find out the first partial derivative first without the origin. So this is simply algebra. So I will do the first thing concretely. If we're differentiating respect to x, then you see that we differentiate the numerator first and then the denominator divided by the denominator squared. And after a bunch of algebra, which I again encourage you to do it, it'll be this guy, x4y plus 4x squared y cubed minus y5 divided by x squared plus y squared squared. And the same argument holds for fy. The third part C, asks you to find fx and fy at the origin. And those are not directly applicable using this kind of nice rule, like quotient rule, product rule, chain rule, due to the fact that it is not really useful, because if you plug in 0 here, it is not defined, right? 0 divided by 0 is not defined. So in this case, we just apply the definition. The definition of fx at 0, 0 is defined to be a perturbation at the x-coordinate subtract by f0, 0 divided by h, right? However, f0, 0 by definition is just 0. And if you plug in this guys to the definition of the function, it is again 0. So regardless of what h is, the numerator is always 0, making the limit 0. So that basically means that the partial differentiation of f at in the direction x at 0 is simply 0. And the same argument holds for y. So that shows that this function has all partial derivatives at any point, whereas if you are not dealing with origin, then you have these two formulas. And if you're dealing with origin, then it's always 0. Now, part D asks us to show that the mixed derivative fxy is actually -1 and fyx is actually 1. So again, simply by definition, fxy at the origin is given by fx perturbing the y coordinate, right? Because you do x first and then y. And then subtract by fx 0, 0, which again is 0 by part B. And this guy is given because 0, 0, 0h is not the origin, right? So you can apply this formula here, and you get this large thing. Ooh, this large thing. 0, 4, h plus 4, 0 square h cubed minus h5. Now, if you pay attention, this guy is 0, right? This guy is also 0. So what you get is minus h5 divided by h4 divided by h, which gives us minus 1, regardless of what h is. So you get minus 1 as a partial differentiation of xy as 0, 0. And the exact same argument works for fyx, which you get 1, because this is h5 divided by h5. So this provides an example where fxy at the origin is not the same as fyx at the origin. What goes wrong? I thought Claire's theorem states that they should be the same. But the problem here is that this kind of precondition is not satisfied. Fyx and fxy actually is not continuous. So if you do the painful algebra, I should mention this first. Part E asks you why it is not true. Does it contradict Claire's theorem? So it does not, in a sense that if you write down the differentiation, after some painful algebra, you get this guy. fxy and fyx are actually the same, ignoring the origin. It looks like this. And this function is actually not continuous because you can see that, as we mentioned in the previous video, that both the denominator and numerator behaves like the degree 6 polynomial. So they actually balance each other out, meaning that you cannot find a limit at origin because you will get different directions along different curves. So it is not continuous at origin, which makes the previous fact that these two guys are not the same not a contradiction towards Claire's theorem. Because Claire's theorem tells you that provided continuity of the mixed derivatives gives you the same fxy and fyx, which in this case does not satisfy. So this is just a quick demonstration of why it is not continuous. Say I goes along some direction y equal to 2x, then you can actually get some number which is not minus 1, which is the definition, which is the derivative of xy at the origin. So again, let me just mention this. Claire's theorem tells you that provided both fxy and fyx are continuous, obviously exist, then those two guys will be the same. But there will be a function that does not satisfy this condition, and therefore concluding that those two differentiation are not the same, right? But most cases in our class where we are treating polynomials, exponentials, those are nice functions. After arbitrary differentiation, you can still get a continuous function, making every mixed derivative the same. fxy is equal to fyx, fxxy is equal to fyxx, okay? All right, that's a lot. So let us conclude this final example. This is a nice little example that might foreshadow what you guys will learn afterwards. So after dealing with, I guess you guys have dealt with differential equation when you are doing calculus 1, calculus 2, or some linear algebra. In this case, we're trying to teach you guys a partial differential equation, meaning that we're dealing with partial derivatives. So first of all, let me define, this is called a Laplace operator, a triangle. It's defined to be the second partial derivative of each coordinate. So if you're not familiar with like this high dimensional notation, you can just regard it as something like this, or something regarding x, y, and z. Okay, so we say that a function u satisfies this equation. So Laplacian is called Laplacian of u, which is simply uxx plus uyy in a two-dimensional setting. So we say that this is 0 for every point inside some domain to be the Laplace equation on this domain, okay? And now this example is asking to verify several functions that satisfy this equation, obviously through computation. So for the first problem, I ask you guys to solve uxy to be ln x squared plus y squared, and I want you to show that it satisfies this Laplace equation in a domain on the whole space without the origin, because this function is not defined on the origin, right? The same thing happens for a high dimensional space. Again, if you're not familiar with the annotation, just set n to be 3. It'll be good enough. So I define the function u to be the length of x in the vector, taking the power to the 2 minus n. For example, in the case n equals to 3, this is minus 1, right? So the function u x y z is simply x squared plus y squared plus z squared. Okay, it's a function in three-dimensional space. And you can generalize it to n equals to 4, 5, 6. And I claim that this function, again, satisfies this equation um, without the origin. Because obviously you can define it at origin, it will result in some 0 in the denominator, right? Okay, now let's try this. For the first function, ln x squared plus y squared, you can do the differentiation. With respect to x, you get, first of all, by chain rule, you have 1 over x squared plus y squared. Then you differentiate the interior function by x, which you get 2x. The same thing happens for y. And now if we do the differentiation again, uxx will be using the quotient rule, x squared plus y squared in the denominator, and 2 is a derivative of 2x. 2x is a derivative of x squared plus y squared, which you get 2 times y squared minus x squared divided by x squared plus y squared squared. And the same logic works for y, which you get this guy. And then, obviously, when you add those two things up, you get 0, right? Meaning that the Laplacian of u defined by this equation is in fact 0. All of those argument works for every point except the origin point. So we verify that this kind of function does satisfy this nice equation. Secondly, for the high dimensional space, we recall that as I mentioned, the distance of x and 0, or just the length of 0, or just the magnitude of this vector 0, x is defined to be x squared all the way up to xn squared taking square root. So basically, the definition of Ru is simply this guy, written down in terms of every variable. X squared plus all the way to xn squared to the power of 1 minus n over 2. So again, I encourage you to try the case where n equals 3, so you guys are more familiar with what we're talking about. But I just want to demonstrate that um, this kind of abstract notation should be able to benefit your understanding on this type of concept. So for now, if I differentiate u regarding to xi, so obviously you can write it down like this, uxi. Then again, by chain rule, we first drop the power. So drop the power. You subtract the power by 1, right? And then we differentiate the interior function, which you get 2xi. Other things like x1 to xn is a constant. So say xi, we're dealing with x2, then x1, x3, all the way to xn is just constant. So we don't have to deal with those guys. And now let us apply this again. If we differentiate this again by xi partially, then again, we have a product rule. This is a function, and it's another function. For the first function, you again drop the exponent, and you subtract the exponent by 1. And you have an extra chain rule term, which results in 2xi squared. And then to differentiate the latter term here, you simply have 2, right? Now, let us write this back in terms of the magnitude, which is much more easier to understand. So first of all, there is a 4 here, a 2 and 2, right? So you multiply by 2, you get 1, 2 minus n, and minus n, which by replacing the minus signature, you get n times n minus 2. This guy is actually the magnitude of x squared. So you get the magnitude of x minus n minus 2. And then this guy is just xi squared, right? Similarly, in this case, we plug 2 here, so you get 2 minus n, which is minus n minus 2. And similarly, this guy is simply the magnitude of x to the minus n. Sorry, I shouldn't put it 2. Okay, so now we have a nice formula for the double derivative of u. Let us try to sum that up to see whether it vanishes or not. So the Laplacian of u is defined to be the double derivative of u along x1, x1, x2, x2, and xn, xn. So we replace this guy in the summation here. The only thing that is summing is actually this guy, xi, right? Everything other than that does not depend on I. So first of all, this guy is a constant. You sum it up n time, you get n times n minus 2 to the magnitude to the vector magnitude. And sorry, I keep writing 2 here. Let me erase those first. Okay. And then this guy is a constant, so you can move it outside the summation and then sum this up. Coincidentally, this guy is simply the magnitude squared, right? So you see that these two guys actually the same because minus n minus 2 plus 2 is just minus n. And that coincides with this guy. So everything vanishes. And again, just as the dimension 2 case, this all of this case actually works when the point is not the origin. So we have verified that this type of function is in fact a solution towards this Laplace equation disregarding the origin. All right? And you might ask, why is the case where dimension is larger than 3 different from 2? You can see that actually, this formula does not work in 2 because when n is 2, this is 2. So 2 minus 2 is 0. It just gives you a constant, right? Obviously, constant satisfy this equation because it becomes 0 when you are differentiating, but it is of no interesting fact. So this is the function that we are more curious about. Both of these functions are called the fundamental solution of this Laplace equation in a sense that you can generate other solutions via these two particular functions. So that is not an important fact. I just want to demonstrate an application on double or higher dimensional derivatives. Okay, wow, that's a lot. So let's go back. So what we have done in this video is that we introduced a definition of partial differentiation, which you can view them geometrically as a slope by fixing y or fixing x, and you have the slope along the x direction towards z or the y direction towards z. And we figure out that to evaluate the total derivative, you simply treat the other variable, which is not in question, to constant, and then differentiate the variable that we are interested in. And next, we introduce the higher order differentiation, which involves x, xy, yx, and y squared. And be careful with the notation. This is x, yx, and this is xy, which we have concluded that does not really matter if f is nice enough. When fxy and fyx are continuous, then all of those second order mixed derivatives are the same. And we have demonstrated another counter example in which it does not satisfy the condition of Claire's theorem, so you have different mixed derivatives. Lastly, we have an example about a partial differential equation, which is a Laplace equation, and we verified that two particular solutions of this equation. I would encourage you guys to try exercising this chapter because you guys should be familiar with differentiation in a single variable version, and that also carries on to the partial derivatives in this multidimensional version. Right. I will see you guys, I think it's next week on 14.4. So yeah, have a good weekend.